When you look up at the night sky, after the day has finally gone quiet, the first feeling is usually wonder. But if you stay there a little longer, another feeling appears, a kind of pressure in the mind. Because those lights are not just lights. They are not tiny decorations above your roof. They are suns. Enormous physical things. Hot matter squeezed by gravity. Places where atoms are being forced into new arrangements, and light is being thrown into space. And around many of those suns, there may be planets. Some rocky, some frozen, some wrapped in thick atmospheres. Some may be carrying oceans. And then the question almost asks itself, if there are so many places where chemistry can happen, and so much time for nature to try things, why does the sky feel so quiet? I do not mean that question in the movie sense. Not green faces, not bright saucers, not a shadow moving behind a cloud. I mean it in the plain physical sense. If intelligent life exists somewhere else, and if some of it becomes technological, why has nobody clearly crossed the dark and reached us? Why is Earth not already just one more known address in the galaxy? That sounds like a question about aliens. But very quickly, it becomes a question about machines, about engines, about heat, about distance, about how much punishment matter can take before it breaks. Now imagination wants to run ahead. Maybe they are hiding. Maybe they are watching. Maybe they came before us. Maybe they never existed. Fine. We can think about those ideas later. But before we make a story, let us make the problem smaller and more honest. Forget the alien for 10 seconds. Think about the ship. Think about a real object with mass. Metal, instruments, fuel, wires, shielding. It has to leave one star and arrive at another one. Not in a dream, not in a drawing, but through actual space. And actual space is not impressed by intelligence. That is the first trap. We hear the word advanced, and we quietly imagine the limits going away. But advanced does not mean unlimited. A civilization 1,000,000 years older than us may know physics far better than we do. It may build engines we would barely understand. But if the engine does work, it makes heat. If the ship moves fast, it needs energy. If it has mass, it resists being accelerated. If it crosses space, it can be hit by things. Nature does not say, "You are clever, so the bill is canceled." The bill is still there. Only now, the numbers may be enormous. This is why Fermi's little question still bothers us. It did not begin as a grand announcement. It began almost casually. At lunch, Enrico Fermi was talking with other physicists in 1950, and the subject drifted toward flying saucers and life elsewhere. Then he asked the simple thing, where is everybody? I like that question because it is not fancy. It has no decoration. It just puts two facts next to each other and lets them rub against each other. The galaxy is old. The galaxy has a huge number of stars. And yet, we do not see clear evidence of visitors from another star. That does not prove we are alone. Be careful there. Silence is not proof, but silence is a clue that the problem is not as easy as imagination first makes it feel. Let us bring the scale down to something we know. The moon looks close. You can stand outside and see it with your own eyes. Light comes from the moon to Earth in a little more than 1 second. 1 second sounds almost nothing. But getting people there required a mountain of engineering, rockets taller than buildings, tanks of fuel, guidance systems, thousands and thousands of people solving tiny problems that could kill the mission. So even our nearest neighbor was not easy. Mars is worse, because Mars is not waiting still in the sky. Earth moves. Mars moves. The spacecraft moves. You do not aim at where Mars is. You aim at where Mars will be. That is already a hard dance. Now jump from Mars to the nearest stars. Alpha Centauri is more than 4 light years away. 4 sounds small. That is the dangerous part. 4 steps is nothing. 4 minutes is nothing. 4 apples fit in your hand. But 4 light years is not small. Light itself, moving about 300,000 kilometers every second, needs more than 4 years to cross that gap. And a spacecraft is not light. It is a thing, a heavy thing. It must be pushed, protected, powered. And if it wants to do more than rush past the destination, it must slow down when it gets there. That last part is where many simple pictures break. In a story, the ship goes fast, and then the scene changes. Suddenly it is at another star. But physics does not skip the boring middle. If you arrive too fast and cannot brake, you did not visit the star system. You only pass through it like a bullet through a dark room. A real visit means control. You can enter orbit, take measurements, send probes down, maybe land, maybe build something. And that means the energy problem comes twice. First to speed up, then to slow down. That is not a small detail. It is the difference between a flyby and a journey that actually means something. So, if someone says, an advanced civilization could travel at half the speed of light, I would not begin by saying impossible. I would begin by asking for the receipt. How massive is the ship? What pushed it up to that speed? What fuel did it use? Where did the waste heat go? How did it avoid cooking its own engines? How did it protect the front of the craft? And how did it slow down at the other end? These are not negative questions. They are the questions that turn fantasy into physics. If the answers exist, wonderful. But the answers have to pay the cost. Then there is dust. And dust sounds harmless. A little grain floating in space seems like nothing. If it lands on your sleeve while you are standing still, you brush it away. But speed changes what small things mean. At ordinary speed, dust is dust. At a large fraction of the speed of light, a grain of dust becomes a violent impact. Not because the grain is impressive, but because the ship is rushing into it so fast. So empty space is not perfectly gentle. It can be thin and still dangerous. A fast ship turns even rare particles into serious problems. Signals have their own problem too. Suppose another civilization sends a message. That message cannot arrive instantly. It spreads outward at the speed of light. And as it spreads, it becomes weaker. By the time it crosses years or hundreds of years or thousands of years of distance, it may be faint, badly aimed, or simply not sent during the tiny slice of time when we are listening in the right way. So quiet skies do not automatically mean empty skies. They may mean distance, timing, weak signals, cautious civilizations, short-lived civilizations, or travelers who discover that the trip is too expensive to make, often. That is why I would not begin this question with aliens as characters. I would begin with aliens as physical systems. If they exist, they must build with matter. If they travel, they must move mass. If they build engines, those engines must handle heat. If they send signals, the signals weaken with distance. If they cross interstellar space, their machines must survive time, radiation, impacts, errors, and the simple fact that nothing nearby is really nearby. So when we look back at the night sky, maybe the silence feels different, not necessarily comforting, not necessarily frightening, just clearer. The stars may be homes, but they are also distances. A distance is also a delay. A delay is also a test of machines and patience. And a journey between stars is not just a decision. It is a negotiation with energy, heat, time, and survival. So before we ask why no one has knocked on Earth's door, we should ask something simpler. How hard is it to reach the door at all? And when we ask it that way, the mystery does not disappear. It becomes sharper, less like a rumor, and more like a real calculation waiting to be understood. Let us take the word distance seriously for a moment, because I think this is the first place where our imagination quietly tricks us. We say the moon is far, Mars is far, another star is far. And because the same word appears in all three sentences, the mind begins to treat them as the same kind of problem. But wait a second. That is already a mistake. It is like saying a match is hot, a kitchen stove is hot, and the center of the sun is hot. Same little word, completely different world behind it. The moon is not far in the same way Mars is far. And Mars is not far in the same way another star is far. The moon is almost our front yard by cosmic standards. Mars is across the solar neighborhood. But the stars are not just houses farther down the road. They are another scale altogether. And if we forget that, if we throw the moon, Mars, and Alpha Centauri into one mental basket, then the alien question becomes confused before we even ask it properly. Start with the moon. It is about 384,000 kilometers away. Now, to a person standing on Earth, that is an absurd distance. You cannot drive it. You cannot sail it. You need rockets, guidance, fuel, life support, and a very serious respect for small errors. But light crosses that same distance in just a little over 1 second. So when you look at the moon, you are seeing it as it was just over 1 second ago. That delay is tiny for ordinary life. Small enough that astronauts could still talk with Earth. Small enough that commands and corrections still made human sense. But even there, even with our nearest big neighbor, space is already teaching the rule. Nothing arrives instantly. A voice has to travel. A command has to travel. Help has to travel. And that 1 second only feels gentle because the moon is still nearby. Now move outward to Mars. And here I want to slow down because many people picture Mars as if it were a red target hanging still in space. It is not. Mars is moving. Earth is moving. Both planets are falling around the sun all the time. So a mission to Mars is not like pointing at a city and driving straight toward it. It is more like trying to meet a runner on a circular track while you yourself are also running on another circular track. You do not launch just because the rocket is ready. You launch when the geometry gives you permission. When the energy cost is not ridiculous. This is the part people often skip. Far does not simply mean many kilometers. Far means timing. It means waiting for the planets to line up in a useful way. It means your machine must arrive, not where Mars is now, but where Mars will be months from now. Miss that rhythm, and the universe does not care how enthusiastic you are. The trip becomes harder, and even Mars, strange as this sounds, is still local. I know that feels wrong at first. Mars feels impossibly far to a human being. But physically it is still part of the Sun's family. A spacecraft traveling to Mars is still moving inside the Sun's gravitational neighborhood. Difficult. Yes. Dangerous. Yes. Expensive. Yes. But still local. Interstellar travel is not Mars travel with more zeros added. That is the trap. It is not the same problem made larger. It is a different problem. The useful landmarks thin out. The travel time stretches beyond one person's career, often beyond one person's life. And if you want the journey to happen fast enough that the launch still means something when the craft arrives, then the energy bill becomes frightening very quickly. Take Alpha Centauri, the nearest stellar system to our Sun, a little more than 4 light-years away. That phrase can sound almost gentle. 4 light-years. It has a nice sound, almost poetic. But it is not poetry. It is distance. It means that light itself, the fastest thing nature allows for carrying signals, needs more than 4 years to cross that gap. So if someone there heard us today and answered immediately, we could not hear the reply for more than 8 years. Not because the antenna's bad. Not because somebody forgot to upgrade the equipment. That is simply the speed limit of cause and effect. The universe is saying, this is how fast conversation can go. No faster. Now, put a real machine into that distance. Not a dot on a diagram. Not a clean arrow drawn between 2 stars. I mean an actual machine with mass, wires, joints, computers, instruments, power supply, shielding, things that expand and shrink with temperature, things that age, things that break. Already the clean picture becomes messy. And if there are living beings inside, then you are no longer sending only a spacecraft. You are sending a tiny piece of earth, air, water, food, waste systems, medicine, heat, repair tools, and some way for minds and bodies to stay healthy inside a metal island for years or centuries. You cannot pull over. You cannot open the window. You cannot call the mechanic in the next town. Between stars, there is no next town. Here is the hard part, and I want to say it plainly. Distance turns into a bill. If you cross it slowly, you pay with time. If you cross it quickly, you pay with energy. There is no free version of the trip. If a spacecraft goes twice as fast, its kinetic energy does not merely double in ordinary classical mechanics. It becomes 4 times larger. If it goes 10 times as fast, the energy becomes 100 times larger. That little square looks harmless when written on a board, but engines do not experience it as harmless. Fuel tanks do not experience it as harmless. Structures do not experience it as harmless. And when the speed becomes a large fraction of light speed, the simple classical picture is not enough anymore. Relativity comes in, and nature stops, letting you pretend that speed is just another number you can keep increasing. This is why sending a signal and sending a visitor are not remotely the same thing. A radio signal is information. It can move at light speed, and even then it weakens, spreads out, arrives faint, maybe at the wrong frequency, maybe during a century when no one is listening properly. That alone is hard enough. But a visitor is matter. Matter must be pushed, protected, guided, powered. And then, this is the part that sounds obvious only after you say it. It must be slowed down. A probe that screams through a star system at enormous speed has not really arrived in the useful sense. It may take pictures. It may grab measurements, but it cannot settle quietly into orbit. It cannot land gently. It cannot spend years studying a planet like a patient scientist. To do that, it must remove the very energy it worked so hard to gain. So the trip has 2 bills. One for leaving, and one for arriving. And the space between stars is not a clean, empty hallway. Yes, compared with air, it is almost unbelievably empty. But empty does not mean harmless. There are atoms out there, dust grains, ions, magnetic fields, cosmic rays, bits of the galaxy that become serious when you hit them fast enough at low speed. These are engineering problems. At high speed, they become something harsher. Your ship is not just passing through the universe. It is running into the universe in front of it. So you add shielding. But shielding has mass. More mass needs more energy. More energy often means bigger systems. Bigger systems add still more mass. And there is the loop. Not a dramatic curse. Not science fiction pessimism. Just matter, keeping accounts. Radiation is quieter, but it may be even more stubborn. On Earth, we live under protection so constant that we forget it is protection at all. Atmosphere above us. Magnetic field around us. a planet quietly absorbing many of the things that would otherwise hurt us. In deep space, that kindness is gone. Energetic particles can damage electronics, change materials, break chemical bonds, injure living tissue. A machine built for a few months is one problem. A machine expected to remain reliable for decades or centuries is another. A crewed ship is harder again. Because now you are protecting bodies, memory, health, judgment, and perhaps a whole little society inside the machine. That is not just transportation anymore. That is survival stretched across distance. So when we ask why aliens have not reached us, I think the first answer should be calmer than the usual answer. Maybe the silence does not immediately mean nobody is out there. Maybe it means reaching anybody is hard. A civilization has to know Earth is here, has to think Earth is worth the cost, has to send something across light years, has to keep that thing working, protect it, steer it, power it, slow it down, and do all of that while the target world changes during the journey. Earth is not a fixed museum display waiting under glass. Climates shift. Species disappear. Civilizations appear late. And our radio noise has existed for only a tiny blink compared with the age of the galaxy. So the silence feels different now. At least to me. It does not feel like a simple verdict. It feels more like a warning label printed on the universe. Distance is expensive. Time is slow. Machines break. Bodies are fragile. And matter is a very inconvenient thing to move across the dark. Not impossible. I am not saying impossible, but not easy. Not casual. Not the way our stories often imagine it. Before we ask whether aliens want to visit, we should ask whether visiting is practical at all. Before psychology, before sociology, before speculation, there is speed, energy, time, and distance. And behind all of them is the strict little accountant of physics. Every change in motion has to be paid for. That is where the next question begins. Not with aliens strolling across a room, but with something much harder. How do you move a tiny world through interstellar darkness? And what must you spend to make it arrive alive? Now let's slow down for a moment. Because this is where the dream of alien travel stops being a movie scene and becomes a physics problem. I don't mean that in a cold way. I mean it in the honest way. If you want to move a spacecraft, you have to change its momentum. And to change momentum, something has to push against something else. A rocket does not simply decide to go forward. It throws something backward. Hot gas, ions, plasma, and photons. Whatever clever engine you choose. But the trick is always there. The ship gets motion by paying for it with something else. There is no free push hiding in empty space. That is the first thing to get clear, and this sounds simple at first. Almost too simple. You say, fine, build a better engine. Use better fuel. Make the ship stronger. But then you take out the pencil, and the pencil is not impressed by excitement. It asks one boring question. How much must the ship change its velocity? That is what physicists call delta V. It is not a magic word. It just means how much speed and direction you must add or remove. If you leave a planet, you need delta V. If you aim toward another world, you need more. If you want to slow down when you arrive, you need it again. And if you want to come home, well, the universe does not give a discount because you already suffered once. Every change in motion has its own bill. Here is the part people often miss. Fuel is not only the answer, fuel is also part of the problem. Before you burn it, it is cargo. It has mass. It has to be carried. It has to be pushed. It has to be protected. So if your ship needs more fuel to go farther, that extra fuel makes the ship heavier. And now you need more fuel to move the extra fuel. And then maybe more fuel to move that fuel too. You see the loop? It is like trying to cross a lake by carrying more and more water on your back because you think water will help you travel. Some of it helps. But before it helps, it weighs you down. That is the trap inside the rocket equation. So when someone says, just build a bigger rocket, I want to pause right there. Bigger is not automatically better. A bigger tank is also something you must accelerate. A stronger structure is also mass. More shielding is also mass. More engines are also mass. You are not just adding capability. You are adding burden. And the ship has to drag that burden with it before any of it becomes useful. That is why interstellar travel is not just a question of ambition. It is a bookkeeping problem written in momentum and mass. Now maybe you say, all right, forget chemical rockets. Give the aliens something better. Ion engines, fusion drives, antimatter engines, laser sails. Good. Let's give them every serious idea we can imagine without pretending magic is physics. The engine names change, but the questions do not disappear. Where does the energy come from? What is being thrown backward? How do you stop at the destination? How do you keep the ship from melting? How do you protect it from dust? How do you aim something across light years when the target itself is moving? This is the uncomfortable thing about physics. It lets you dream, but it also asks for receipts. Then relativity walks into the room, not as a fancy idea, but as a speed limit with teeth. Light moves at about 300,000 kilometers per second in vacuum. A spacecraft is made of matter. It has rest mass, and matter cannot be pushed all the way to light speed. As it gets closer and closer, the energy needed to push it faster grows enormously. You do not just need a slightly better engine. You run into the structure of space-time itself. And that is not the same as saying travel is impossible. It means the price rises in a way that does not care about our impatience. Faster than light. Sounds like the easy escape hatch. And I understand why people like it. It solves the emotional problem of distance. But known physics does not let ordinary matter or useful signals simply outrun light through space. There are mathematical ideas people discuss. Warped spacetime, wormholes, exotic geometries. But those are not the same thing as working engines sitting in a hangar. They require conditions, We do not know how to create or control. So the honest answer is not never. And it is not, of course they can. The honest answer is, under established physics, faster than light travel is not available as a normal transportation method for matter. Let's stay below light speed then. Suppose a civilization can reach 10% of light speed. That is already unbelievably fast by human standards. But even then, Alpha Centauri is not next door. It is still a journey of decades if you ignore acceleration and braking. And you cannot ignore those. A real ship does not blink into cruising speed. It must accelerate. Then later it must slow down. If there are living beings inside, the acceleration must not crush them. If there are machines inside, then the structure must survive stress, vibration, radiation, heat, and impacts. The faster you go, the less gentle the universe becomes, and dust becomes serious. At walking speed, a grain of dust is nothing. At a large fraction of light speed, it is not nothing anymore. It is a tiny projectile meeting your ship with frightening energy. So now, shielding is not decoration. It is not an optional shell. It becomes part of the mission. But shielding has mass, and mass brings us back to propulsion. You see how the problems talk to each other. Speed demands energy. Energy creates heat. Heat needs radiators. Radiators add mass. Mass demands more propulsion. It is not one wall. It is a room where every wall is connected to the next. Heat is especially unforgiving. A spacecraft cannot cool itself the way a car does by giving heat to the air. In deep space, there is no air to carry the heat away. The ship must radiate heat as light. That means surface area, materials, temperature control, big fragile structures that must survive the same journey. So when you imagine a powerful alien engine, do not only imagine the bright exhaust, imagine the waste heat too. Imagine the ship trying not to cook itself while crossing a distance so large that even light takes years. And even if all of that works, there is another question. Where exactly are you going? A planet seen through a telescope is not a place you know perfectly. It is a message from the past. If it is 1,000 light years away, you see it as it was 1,000 years ago. If it is 10,000 light years away, you see an even older version. So, a civilization choosing targets is not choosing from live photographs. It is choosing from delayed evidence. Maybe the world changed. Maybe the signal ended. Maybe the interesting thing is no longer there. That changes the alien question. Maybe they are not absent. Maybe travel is rare. Maybe signals are cheaper than ships. Maybe probes are sent only to very special targets. Maybe Earth has not looked technological for very long. For most of Earth's history, there were no radio transmitters, no industrial lights, no spacecraft, no obvious sign that a species here was building instruments and asking questions. Life is old. Technology is young. From far away, Earth may still look like forests. oceans, clouds, and ordinary biology. So when we ask, where are they? Maybe we should first ask a quieter question. How hard is it to arrive? Not in a story, but in matter, in energy, in heat, in time, in risk. The answer may be simple and severe. Between existing somewhere and arriving here, there is physics. Mass makes you pay. Speed makes you pay. Heat makes you pay. Distance makes you wait. And perhaps the sky is quiet not because the galaxy is empty, but because crossing it is not casual. It may require patience on a scale that makes even an old civilization think twice. Now let us pull the camera back a little. Because when people ask why aliens have not reached us, they usually picture the exciting part first. The ship. Some enormous machine crossing the dark between stars. Maybe with engines glowing. Maybe with strange beings inside. That is the image our minds like. Because it is simple. It is dramatic. And it gives the question a clear shape. But I think it starts too late in the story. A starship is not the beginning of the problem. It is the last visible piece of a much longer chain. Before there is a ship, there has to be a civilization. Before there is a civilization, there has to be some stable place where life can last long enough to become clever. And before any of that matters, there has to be energy flowing in the right way, memory being preserved, tools being improved, and generations that do not lose the thread. That is easy to say, but it is a huge demand. Intelligence is not a magic door into the galaxy. It is matter arranged carefully enough to think. And matter is always under pressure from heat, damage, decay, accident, and time. So the deeper question is not only, can a machine cross the distance? It is this: can the world that built the machine remain steady long enough for the journey to mean anything? That may sound less exciting than a starship, but it is more honest. A planet is not a clean table in a laboratory. It is noisy, restless, always changing under your feet. The air changes. Oceans move heat around. Volcanoes open the ground. Asteroids sometimes arrive without warning. And the star above the planet slowly changes over immense time. Life has to live inside that moving machinery. It has to copy itself again and again, while chemistry keeps trying to scatter things back into disorder. Then one day, if everything goes strangely well, some form of life begins to build tools. Then the tools become machines. The machines become instruments. The instruments become a way of reading the sky. And only after all of that does the idea of another star become a real engineering question. You see the difficulty? It is not one miracle. It is a whole staircase of unlikely steps. Miss one step badly enough, and from far away that world looks silent. I do not want to make the easy argument here. I am not saying every civilization must destroy itself. That sounds powerful, but it is too neat. Nature is rarely that tidy. A civilization may fail dramatically. Yes, but it may also simply slow down, turn inward, lose the need to expand, become careful with energy, or spend a very long time learning how to live around its own star. Think about our own solar system for a moment. It has planets, moons, asteroids, comets, metal, ice, sunlight, and an absurd amount of empty space. A civilization that masters even one star system may have more room than it knows what to do with for a very long time. So before crossing to another star, it might build habitats, move small bodies, collect energy, and become very good at staying alive locally. That is not failure. It may be the sensible thing to do. Interstellar travel may be possible, but not urgent. And from our distance, not urgent can look exactly like silence. Here is another way to picture it. Not as a galaxy full of neighbors, ignoring one another, but as islands separated by time. These are not islands with water between them. They are islands separated by slow light. Expensive missions, uncertain targets, and histories that may not overlap. On one island, some beings may be looking upward for the first time. On another, machines may be listening quietly. On another, life may still be microscopic and invisible, except through chemistry. On another, a civilization may have existed before humans ever made fire. That is the uncomfortable part. They can all be real and still never meet. A sky full of stars does not mean a sky full of reachable places. The galaxy can be rich with possibilities and still be poorly connected. Then comes the question of cost. Why send a large physical mission across light years at all? If you want knowledge, telescopes are cheaper than ships. If you want to send information, light is cheaper than bodies. If you want materials, your own system may already have more than enough for a long time. This does not remove curiosity. Curiosity is real, but curiosity still has to pay the energy bill. Every kilogram you push toward another star has to be accelerated, protected, guided, and somehow made useful when it arrives. That is why small probes make more sense than giant living ships. A machine can sleep, wake up, check its instruments, correct its course, and survive conditions that would kill a body very quickly. But even a patient machine is not free. It needs power, shielding, redundancy, and most importantly, a target worth the trip. Now imagine such a probe passing Earth 200,000 years ago. It sees a living planet, blue oceans, clouds, forests, animals moving below. But does it see radio towers? No. Does it see city lights on the night side? No. Does it know that one day this world will build telescopes and ask whether it is alone? Probably not. It came too early. That is all. No villain. No mystery empire. Just bad timing. And bad timing matters enormously in a galaxy this old. Our radio age is only about a century old. To us, a century feels large because we live short lives. But compared with Earth's history, it is not even a chapter. It is a mark in the margin of a very thick book. For almost all of Earth's life, this planet was alive, but not listening. It had oceans, but no radio telescopes. Forests, but no mathematics. Animals, but no spacecraft. That should make us a little more humble when we ask why nobody has answered yet. There is also a strange problem with seeing across space. Light tells you what a world was, not what it is right now. A probe arrives later, sometimes much later. So you aim at the past, but you arrive in the future. Say that slowly, because it changes the whole picture. If another civilization sees a distant planet with oxygen and water vapor, that is interesting. But it is not the same as seeing someone ready to talk. If they send a probe, the planet may change before the probe gets there. The biosphere may still be simple. The intelligent species may not have appeared yet, or it may have appeared and vanished in the meantime. The farther away the target is, the more uncertain the meeting becomes. Contact is not like knocking on the next door. It is more like trying to meet someone across history and hoping both sides are awake at the same moment. There is one more possibility that does not require any drama. Maybe advanced civilizations become harder to notice because they become efficient. A young civilization leaks energy everywhere. Radio waves, city lights, waste heat, messy industrial signals. But an older civilization might use narrow beams instead of broadcasting everywhere. It might keep most of its activity local. It might waste less energy, because waste is still a physical cost. We should not assume that advanced technology must be loud. Sometimes advanced means quiet. Not mysterious, quiet. Just efficient, quiet. From very far away. Competence may be hard to distinguish from absence. Put all of this together, and the silence becomes less simple. The universe does not have to be empty to look empty from here. It only has to be large, slow, expensive to cross, and badly timed. Two civilizations can both exist. Both look up, both wonder, and still miss each other completely. Not because they are foolish, but because light is slow and life is fragile. If contact ever happens, I do not think it will feel casual. It will mean many things had to go right first. Life had to appear somewhere. It had to keep going long enough to become curious. It had to build instruments, send or receive a signal, and arrive at the tiny window when another mind was actually listening. That is the hard part. Not simply building a ship, but having the right world on the right time, the right signal, and someone awake on the other end. Now we come to the quiet part of the question. And I want to be careful here, because this is where people usually become too certain too quickly. Some people hear the silence of the sky and say, "There must be nobody out there." Other people hear the same silence and say, They must be hiding, or watching, or choosing not to speak. But both answers may be too fast. The honest answer is smaller, and it is probably the most scientific answer we have. We do not know yet. That is not a failure. That is the beginning of clear thinking. Science does not become strong by pretending the dark is already filled with answers. It becomes strong by saying, "Wait, what do we actually know?" We know no alien civilization has reached us in a way we can clearly recognize. That is all. It does not prove life is absent. It does not prove intelligence is rare everywhere. It does not prove Earth is the only little place where atoms learn to ask questions. It only tells us that contact has not happened here, in our time, in a form we can measure, and that smaller sentence is much safer, because once we keep the sentence honest, we can begin to ask what physics is actually saying. And physics says something very plain. The stars are far away. I know that sounds too simple, almost childish. But if you sit with it for a moment, it becomes enormous. The moon feels far to us, but the moon is basically in our front yard. Mars feels like a great adventure, and it is. But Mars is still another room in the same house of the sun. The nearest stars are not like that. They are not across the street, not over the hill, not even across an ocean. They are separated from us by distances so large that even light takes years to make the trip. And light is not a slow messenger. Light is the fastest thing nature allows us to use. So if light itself needs years, then a machine made of metal, instruments, fuel, shielding, and delicate electronics has a very hard bargain to make. This is why I do not like the sentence, "If aliens existed, they would already be here." It sounds logical at first, but it hides too much inside the word already. Already compared with what? A human lifetime, a civilization's lifetime, a galaxy's lifetime. Those are not the same clock. A civilization would have to appear somewhere, survive its early dangers, discover science, develop technology, avoid destroying itself with that technology, choose a target, build a machine that can last for centuries, protect it from radiation, protect it from dust, remove waste heat, steer it through darkness, and then somehow slow it down when it arrives. That is not one problem. That is a long chain of problems. And a chain is not strong because one link is strong. It is strong only if every link holds. Take something ordinary, a speck of dust. On a table, dust is nothing. You wipe it away with your finger, and the story is finished. But in space, if a spacecraft is moving very fast, that little speck is no longer harmless. It can hit like a tiny bullet. And there are many such little things in the dark. Not enough to make space feel crowded, but enough to matter if you are trying to cross huge distances at enormous speed. Then think about heat. This part is less dramatic than rockets, so people forget it. But every engine produces waste heat. Every computer produces waste heat. Every living body produces waste heat. On Earth, we dump heat into air, water, walls, ground. In deep space, you do not have that convenience. You have to radiate heat away, slowly, carefully, into cold darkness. So the question is not only, can you go fast? The better question is, can you go fast and still remain a working machine? And then there is time. Time may be the part that makes the whole thing feel different. Suppose a civilization sends a probe toward another star. Maybe it takes 100 years, maybe 500, maybe much longer. What happens at home while that probe is traveling? People die. Governments change. Languages shift. Cultures forget old priorities. The question that launched the probe may no longer feel urgent to the descendants of the people who asked it. So interstellar contact is not just a problem of engines. It is a problem of memory, patience, and continuity. A civilization has to remain stable long enough to care about an answer that may arrive after the original questioners are gone. That is not impossible, but it is not casual either. It asks for a kind of endurance we have barely begun to understand. So, when we ask, where is everybody? Maybe we should not ask it like an accusation. Maybe we should ask it like a measurement problem. Life may be rare, or it may be common. Intelligence may last a long time, or it may appear briefly and vanish. Signals may be crossing the galaxy right now, but missing receivers by thousands of years. A message could have passed through the solar system before humans had radio, before cities, before writing, before anyone here could know that a message had come and gone. That is not a wild fantasy. That is simply what timing means when the distances are measured in light years. A galaxy can be full of events and still feel silent to a young listener. And I should say this plainly. None of this means we should stop looking. It means the opposite. We should look more carefully. We should listen better. We should build telescopes that can read the atmospheres of distant planets. We should ask, what gases might suggest biology? What patterns might suggest technology? What kinds of signals could survive the trip across space? These questions are not as exciting as a ship suddenly appearing over a city, but they are better questions because they can be tested. A dramatic story can make us feel something for a minute. A testable question can move civilization forward. Slowly. But really. So the answer to why aliens have not reached us should stay careful. Not because they definitely do not exist. Not because they are definitely hiding. Not because the mystery has already been solved. But because crossing the stars is physically hard in many ways at once. Distance stretches the trip. Light limits communication. Energy charges a price for acceleration. Heat must be removed. Dust can damage fast machines. Radiation attacks matter. And time can separate civilizations as strongly as space does. That is not a neat answer. But it is a useful one. It does not turn silence into certainty. It turns silence into a problem we can think about clearly. So, when you look up at the night sky, I would not rush to call it empty. I would also not rush to fill it with easy stories. I would leave the question open, but not vague. The universe is large. Light is slow on cosmic scales. Machines are fragile. And civilizations may not stay ready forever. That may be the most honest place to stand right now. Not at the final answer, but at a better version of the question. We keep listening. We keep measuring. We keep learning how not to fool ourselves. And maybe that is already something rare. A young civilization on a small planet, not yet knowing who else is out there, but still patient enough to ask, and honest enough to wait for evidence,